In Chapter 4, we'll be taking a look at local area networks, also known as LANs. Local area network architectures are determined by Layer 2 of the OSI model, which is the Datalink layer. The Datalink layer provides point-to-point connectivity between devices over a physical connection that's provided by the underlying physical layer. The Datalink layer breaks a data stream into chunks called frames or cells, depending on the network architecture that we're talking about. Most network architectures will be frames, but like the ATM network architecture refers to the chunking at the Datalink layer as a cell. The Datalink layer also provides for reliable communications between devices. And to meet this purpose, it has three key functions: error detection, error correction, and flow control. In LANs, the Datalink layer can be broken down into two sublayers: the Media Access Control, or MAC sublayer, and the Logical Link Control, or LLC sublayer. So again, what we're doing is we're taking the second layer, the Datalink layer of the OSI model, and then we're actually subdividing it into two layers. So on the top sublayer it's the LLC, and the bottom sublayer is the MAC sublayer. We'll show you a graphic later on in this chapter that help you to visualize this a little bit better. Now the Datalink layer also provides the source and destination address for the frames or cells that it's going to put out onto the network. And so again, that MAC sublayer that we're just talking about in the previous slide is really the sublayer that's responsible for this addressing. MAC is the Media Access Control, and so every network card that's manufactured has a MAC address burned onto it. And so obviously this is not to be confused with the Apple Macintosh computer whatsoever. This is something completely different. The acronym again is just for Media Access Control. So in an Ethernet network, a MAC address is 48 bits long. And if you look at a MAC address, in fact a good way to do this is to open up a command prompt and type in ipconfig /all and look for where it says physical address in the results that come up on the screen. That's the actual MAC address of the network interface. And so anyway, it's 12 hexadecimal digits. So it uses the hexadecimal numbering system, so that means that you're going to see letters very often in the address of A, B, C, D, E, or F. And the first 2 bits of the MAC address identify the type of address that it is. The next 22 bits identify the manufacturer of the network interface. And then the last 24 bits are just uniquely generated numbers at the factory. They just uniquely generate the last 24 bits so that makes that particular network card unique in the network that it's going to operate on. So here's an example of a MAC address separated by dashes here. Usually this is the way that it's organized in pairs of hexadecimal numbers. And so again, you can see that both letters and numbers are used here. And then you can see the translation of that MAC address into its binary value in the next bullet. I recommend that you take a look at the video that I have posted for how to use the scientific calculator. That will show you how you can actually type in hexadecimal values into the scientific calculator and convert them over to binary, or vice versa. You can actually type in binary values and then have them converted into hexadecimal values. So take a look at that video if you're not familiar with the hexadecimal numbering system and how numbers get converted back and forth. That won't actually show you the manual method of how they get converted, but it will do the conversion for you. Now every single network segment has to have unique MAC addresses. So that means that every device that's operating in a single Ethernet segment will have to have a unique MAC address, and most likely they will. The chances of duplicating a MAC address are quite large. It is possible, but most likely not going to be the case. So just again, the important thing is each individual device must have a unique address, just like a house must have a unique address on the street that it's on. So same thing with network interfaces. They have to have unique MAC addresses for the segment that they operate on. There are three different ways that data link layer frames or cells can be addressed, and they are broadcast, unicast, and multicast. In the case of broadcast, the destination address would be 12 Fs. Remember that MAC addresses are hexadecimal, and there's 12 digits in a MAC address. So if they're all Fs, that means that that message is being sent to all devices on that particular network segment. And if we translated the all Fs, the 12 hexadecimal Fs, into binary values, then the destination MAC address is all ones. Unicast address is the second type of addressing. That means that the destination address is for a specific device, and so it uses that device's unique MAC address as the destination that it uses for sending the message to. And then in multicast, that means that we're sending to a group of devices, and so those devices, depending on what type of devices we're talking about, but they get registered into a group. And so instead of broadcast, where every single device on the segment receives it, only a selected few, a group that's been predefined within the segment, is going to receive the message that's being sent out. So we're sending to everybody, we're sending to one specific interface, or we're sending to a group of interfaces. That's the three different ways of addressing frames or cells: broadcast, unicast, or multicast. The way that networking works is the devices are listening for messages on the media, and if the destination address for that's of the message that's traveling on the media, if that destination address matches that of the interface, then the interface goes ahead and receives that particular message and then processes it. So generally speaking, most network interfaces will not process messages that are not addressed specifically for their MAC address, although in the case of broadcast, as we talked about earlier, with all Fs as the destination address, then they will process that as well. But generally, as far as the specific address, if it's not specifically addressed to them or broadcast addressed to them, they're not going to process the message. So you can actually set a network interface to what is called promiscuous mode, and that allows that particular network interface then to receive all of the messages that are being transmitted on a particular network segment. So here's a graphic now to illustrate what we've been talking about with regards to MAC addresses. You can see that there are 4 computers, each computer having a network interface, and if you look at the white boxes that are overlapping on each of the computers there, it's showing us here is the MAC address for this particular computer's network interface. So the computer in the top left now is going to send a frame out onto the network, and you can see it's addressed to 00E018AB1290. So as that message then travels into that hub, the hub will actually forward the message out all of the media that's connected to it. So in other words, all of the other wires that are coming out of that hub there will also be forwarding this message, and then each of the computer's network interfaces that are attached to the media will then see that message, but only the computer that has the matching MAC address will actually process that message. So here's the results of what we were just talking about. Again, the computer, the network interface in the upper left-hand corner there, was transmitting a message to a specific MAC address, and that address was of the computer in the upper right-hand corner there. So you see that it accepts the message, and then the bottom 2 computers, having MAC addresses that didn't match the destination of the message. They just simply ignored the message. So we need to define network segments because we use that terminology quite a bit when we're discussing networking. A network segment is just a collection of devices that are all attached usually to the same equipment like a switch or a hub, and they can send messages to each other without the use of another device called a router or a layer 3 device, because remember that MAC or well, the media access control, the MAC address, is a Datalink layer address, so layer 2. And so we're not talking about another type of address that also are added into messages like an IP address. That happens up at the network layer, which is layer 3. And a router is needed to take the information from one segment and forward it over to another segment. So in this case here, it's just a single segment of computers that can all communicate with each other, but can't communicate outside of that segment unless we use a router and unless we use an additional address information, which would be at the network layer, the layer 3. A lot of times you'll hear network professionals refer to a segment of network devices as an IP subnet. And generally speaking, an IP subnet and a segment are pretty much the same. But since we're using the term IP subnet here, we're really referring to layer 3 or the network layer addressing scheme. And so you can actually divide up computers also based on their layer 3 address, their network layer address. So with the use of a switch in modern day networks, it's actually possible to create individual network segments without actually also having them correspond to an IP subnet. So there is a slight difference between an IP subnet and a segment. So just think of a segment as being referring to devices that are operating at the data link layer that are all part of the same collision domain, the same broadcast domain, and we're going to look at those two terms here in just a little bit. Whereas again, an IP subnet is referring to a group of computers that have been divided based upon their layer 3 address, their network layer address. Another important concept of local area networks is what's the difference between a collision domain and a broadcast domain. So a collision domain is a collection of devices that share the same media directly, and only one device that is on the shared media can transmit at a time. If you have more than one device transmitting, then you have what is called a collision, because the two messages, if you had two devices trying to transmit at the same time, the two messages would collide on the media and they would corrupt each other, and neither message would be of any good, of any value at that point because of the corrupted nature of the message. In a broadcast domain, we have a collection of devices that will hear a broadcast message that's sent at the data link layer regardless of the network structure. So if you recall previously when we were talking about MAC addresses, we talked about the fact that a destination address of all Fs is a broadcast address. So when a device sends out a message with the destination of a broadcast address, all Fs, then all devices that are part of the same broadcast domain will receive that message. The use of bridges and LAN switches allow a single network segment to be broken into multiple collision domains, although they remain a part of the same broadcast domain. So in the next couple of slides here, we'll show you some graphics and help to clear that up for you a little bit. So in this graphic, all of the computers that you see are part of the same collision and broadcast domain. And that's because we're using a hub. If you look at the labeling on the device that we connect the computers to, this is a hub or a multi-port repeater, and in that type of a device, when we send a message into the hub just simply forwards that electricity out to all devices that are attached to it. So it's just the same as if they were all connected to the same cable, the same media. So again, if one device were to send a message out, then no other devices could transmit at that point in time. They have to wait until that message cleared the wire, and then they would be able to transmit. So they're part of the same collision domain. And then also, if one of the devices sent out a broadcast message with an all F's destination, then all of the other devices there would also be able to receive that message. So they're also a member of the same broadcast domain. Now in this slide, we've changed things up a little bit. Instead of using a hub which repeats the signal out of all the ports, we're using a device called a switch. And a switch is actually more intelligent than a hub. A hub actually operates at the physical layer. In other words, it just simply forwards electricity. A switch can actually read the data link layer addressing information. So a switch will determine which port to forward a message out of based on the destination MAC address. So in this case, when the top computer there sends a message into the switch will isolate that message between the sending computer and the destination computer. Any other computer attached to the switch can go ahead and send simultaneously. So each computer at this point is considered to be a part of its own collision domain, because all of the computers can actually transmit simultaneously without affecting the message of the other computers. So they're all now on separate collision domains. However, if any one of these computers sends out a broadcast message, one with a destination of all F's, then all of the other computers that are attached to this switch will be able to receive that message. So they're still a member of the same broadcast domain. They're now just separated as far as the collision domain. So here is a brief history of local area network architectures. Back in 1970 at the University of Hawaii, they developed the first network called the Aloha Net, and that was used, it was actually radio based. It was used to transmit between the islands, the Hawaiian Islands, from one island to another. And then later in 1973, Robert Metcalfe came along and helped to develop the Ethernet network at Xerox Corporation. Following that, in 1975, the Digital Equipment Corporation, who was very big in the mainframe environment and one of IBM's big competitors, they developed the DECnet network. Then DataPoint Corporation in 1976, only a year later, came up with their own proprietary networking scheme called ArcNet. And then IBM in 1985 developed Token Ring. Apple in 1985 as well developed Local Talk, and then wireless technology in the commercial sense was developed in 1991, and then really didn't get much action, much activity. It wasn't a popular item until Apple came along and actually enhanced the capabilities of wireless LANs in 1999. So in the previous slide you saw the history of local area networks, and each of those items that were listed there, each one was a different local area network architecture. And architectures are defined by three different properties: how it accesses the network, what its logical topology is, and what its physical topology is. So an access methodology is how a sending device, a transmitting device, determines whether or not it can send a message, place a message onto the media that it needs to transmit the message on. The logical topology is how that message gets transmitted within the media. Is it sequentially sent from one device to the next device to the next device until it reaches its destination, or is it broadcast meaning that it's capable of reaching all devices simultaneously, and then each device determines whether it should process the message or not. And then the physical topology is the actual physical makeup of the network, how all the cabling and the devices and the switches or hubs are all interconnected to each other. And that can be done in a bus fashion, which is kind of a linear fashion, where you take the cable from one network card and you plug it into the cable of the next network card, and then that gets the out of that gets connected to the in of the next network card, and on down the line. So you have kind of like this big long line of cabling that attaches to network interfaces as it goes down the path. A ring topology means that we are also transmitting from one device to the next, but it's in a ring fashion. In other words, the starting point also ends up being the beginning point. In a bus network, that's not the case. The starting point is on one end of the cable, and the ending point is on another end of the cable. The most commonly used physical topology is the star topology. That's where we use the hub or the switch to connect devices to it. So if you can just picture those two graphics that I was showing you earlier when we were talking about collision and broadcast domains, we had the wires coming out of the switch. So the switch was like the central hub of the network, and then we had this kind of a star pattern, almost like octopus arms coming out of the switch. And so that's why that's called a star topology. In a mesh topology, you actually have multiple connections between the devices, and usually you use routers for doing that. Like the internet is a good example of a meshed network where there's multiple connections to simultaneous locations. There is no single architecture that really is determined to be best in all circumstances, although Ethernet is the most commonly used in modern day networks. The network configuration then is going to be the combination of the architecture, which again is the access methodology, the logical topology, and the physical topology. That's the architecture, plus the media that we're using. Are we using fiber optics? Are we using Cat5e? Are we using wireless? So that's the different types of media that is actually where the message is being carried across. So here are a few of the more popular access methodologies. Remember, that's again one of the properties of a network architecture. CSMA CD is the most commonly used these days in Ethernet networks. CSMA CD stands for Carrier Sensing Multiple Access with Collision Detection. And the way that it works is that the sending device basically is attached to the media, and it's listening to the media to see is there already a signal on that media or not. And if it determines that the media is free, then it goes ahead and it sends its message out there. And should there be a collision, it is capable of detecting that a collision occurred. So if we actually have, in the case of really large bus networks, it's possible for the computer at one end of the cable to not detect that the computer at the other end of the cable is sending a message, and so they might both put a message on the wire at the same time. And if that's the case, they will collide with each other, but both sending devices will detect that that collision occurred, and what will happen then is that they will wait, they'll back off their sending for a period of time, each one randomly within the internal workings of the network interface. It just randomly selects a value of milliseconds that it's going to wait for before it retransmits, and so that's a randomly selected value, and so theoretically it's not going to be the same time frame, and so that means that one will transmit before the other one will transmit, and that hopefully will avoid a collision in the next attempt at transmitting. One of the reasons we don't use bus networks these days, though, is that wasn't the most successful way of determining that messages are being sent and when they should be sent. Not to say that CSMA CD was the problem there so much. It's just the fact that we had all of the network interfaces attached to the same media. And then the same is the case with hubs, because a hub just basically internally is a bus topology. So modern day networks, now we use switches. Switches, as I mentioned to you earlier, are intelligent. They have an ASIC chip in there. And ASIC is an acronym. It's Application Specific Integrated Circuit. And that is capable of reading the data link layer addresses and only forwarding the messages then out of the ports where that device, that destination MAC address device, is actually connected to. So we're able to avoid a lot of these collisions by using switches in modern day networks. There was propagation delay, as it says there in the second bulleted item there for CSMA CD, because it does take a little bit of time for the signal from the source to reach its destination. With CSMA CA, this was originally developed for the local talk networks, the Apple local talk networks, and that stands for carrier sensing multiple access with collision avoidance. So in this case, it actually, the sending device would put a little message out onto the media before it sent the actual message it wanted to put out there. And so if that little message that it put onto the media hit something, another message and collided, then the sending device would know to hold off. Problem is there's a little bit more overhead in that particular type of a process because it always has to send this test message before it sends the actual message. So that actually slowed down then the capability of the local talk networks. And then IBM uses token passing. The advantage with token passing is that the transmission device must possess what is known as a token before it can transmit. And so that helped to avoid this collision possibility because only one device could have the token at any given time. And so the token would actually travel from one device to the next at very high rates throughout the day. It just constantly is traveling from one device to the next, and then at any one time any device may have the token, and if it needs to transmit, then it attaches its message to the token and puts it out onto the media. So it actually did ensure the transmission device would have 100% of the channel it was trying to transmit on. But the problem there was you had to wait for the token, and so it really reduced the efficiency and capability of that network. For a long time there was a big battle between whether CSMA CD or token passing would be the predominant access methodology used in networks. And so this graph here is an example of one of the many methods that were used to make comparisons between the different network architectures. And so what it's showing you there is that token ring is actually better as bandwidth demand increases. So CSMA CD was a little bit faster. You get more throughput out of CSMA CD up to about 75% of the bandwidth. But as you got more and more network interfaces on the network, then you were saturating the bandwidth. And so because of the more collisions would start occurring, then CSMA CD would actually drop as far as the throughput because there was a lot of retransmission of the messages because so many collisions were occurring. So token ring was determined to be superior as you got a high density network. But then switches came along. This is back when they used bus networks, and then switches came along, and that pretty much reduced the whole collision capability or possibility in CSMA CD networks. And so that is the access method that we use today most predominantly in Ethernet networks, which is the largest installed base of local area networks out there. So the second property of a network architecture was logical topology, or is logical topology. And so this is the method of delivering the data. We can either go sequentially, in other words, passing the message from one node or one network interface to the next until it reaches its destination. This is also known as a ring logical topology, and so this was used a lot in the token ring networks that IBM developed. The device that sends the message sends it to the next computer in the chain, and then that gets forwarded to the next computer in the chain, and then on until it finally reaches its destination. In broadcast, the data is sent out to all nodes simultaneously. So again, if you remember back to that graphic where we're showing you the hub, then all the devices attached to the hub were able to receive the message as soon as it was sent out. And then each node, each network interface, decided if the data was addressed to it or not. If so, it processed it. If not, it just simply ignored it. And then finally, as far as the network architecture properties are concerned, we get to physical topology. Again, this is the way that all the devices are connected together. And so we've got ring, bus, star, and mesh are the commonly used or known physical topologies. So in ring-based networks, again, the packets are being passed sequentially from one network interface to the next. In bus, it's, as I mentioned to you earlier, a linear arrangement of devices, and there was a terminator at both ends of the cable, so that when the message, the actual voltage is what we're talking about at this point, reached the end of the wire, that it wouldn't reflect back on itself, because that in itself would cause a collision. So terminators are used to actually absorb the electrical pulses at each end of the cable. The biggest problem with bus networks is that if you had any loose connections, then the entire local area network would go down, because you no longer had termination, basically. And so if you can picture kind of a loose connection that's not attached to its interface, you've got the electrical charge then actually capable of reflecting back to itself, and that started causing collisions on the network. So that was the big problem with bus networks. Anytime you wanted to pull a computer off of the network, that would bring the whole network down. They were constantly coming loose from the interfaces, and so bus networks were kind of problematic. Star networks, used in the most modern day networks. The biggest drawback to a star-based network is that the hub or the switch is a single point of failure. If that device fails, then of course the network is down. But the advantage is that in a star-based network, if one device is down or disconnected, it's not going to bring down the entire local area network. Only that device is affected, not any of the other devices that are attached to the hub or the switch. And then finally the mesh, again, multiple paths to a particular source or destination. So the internet, a good example of that. So here's our local area network technology model. A LAN, regardless of its network architecture, requires these components. Has to have some sort of a central wiring concentrator. So that would be a hub or a MAU. MAUs are used in token ring networks. That stands for multiple access unit. A concentrator, which really is a hub, or a LAN switch. So the device that everything is connecting to. Then we've got the media, which is what we connect between the devices. And then we have the network interface cards, also known as NICs. Get used to referring to your network interfaces as a NIC. And that's the physical link then between the PC and the media. And then we have the network interface card drivers. That's the interface between the network interface card and the computer's operating system. And then of course you have to have some sort of a network OS, a network operating system that can control the packaging of the messages and hand it off to the network card, and then also applications that can work over the network as well. Things like web browsers and email clients and all that kind of good stuff. So this graphic here now is kind of putting the whole picture, this is the big picture, putting all those components together for us in one visual. So we have the network interface card driver again, that is the software bridge. The bridge is the hardware and software gap between the network interface card and the network operating system. So if you look at the computer on the left, it's just showing you it has a network operating system installed. In the early days, when we were using like DOS was strictly a computer operating system. It didn't have any network operating system capabilities, and so we used to use other software products like LANtastic. I was remembering one that we used quite a bit. You would actually install LANtastic on top of DOS, and that made DOS computers then capable of having network functionality. These days, your modern operating systems, your Windows and your Apple and Linux operating systems, they all have the network operating system components built in. So you actually have both the computer operating system and the network operating system now built into one single operating system. So the network operating system communicates with the network interface card's software driver. So you have to have a driver installed for the network card, and that does the translation then between the network operating system and the network interface card. And so that's what gives the network operating system the ability to communicate with the network interface card and send messages to it. Then at the network interface card packages the message from the network operating system into a frame or cell in the case of ATM. And so the data link layer is actually part of the network interface card. So it's taken again the message from the network operating system, packages it into a frame, puts on the data link header, which is the source MAC address, the destination MAC address, and also the trailer, which is the error checking methodology. And so then hands that down to the physical layer, where it is just simply a stream of zeros and ones, and then the physical layer converts it into electricity or light pulses depending on the type of media that we're going to be connecting to, and forwards the zeros and ones as a stream out onto the media. The media then is going to transfer the message to a central concentrator, which is some sort of a hub or a MAU in the case of Token Ring, or a switch, which is the modern technology that we use as our central concentrator. And then the central concentrator is going to forward it to the appropriate media on its way to the destination. And then at the destination network interface, we're going to convert the light or the electricity back into recognizable zeros and ones that can be processed at the data link layer. And of course the data link layer at the receiving NIC is going to determine whether the MAC address, the destination MAC address, does indeed match its own MAC address. And if not, ignore it, but if so, go ahead and continue processing, meaning using the network card's driver, send that message up to the network operating system on the receiving machine, and then of course the network operating system and whatever application is running on the receiving end can go ahead and process the message. Now in this graphic we're really making a comparison between two different architecture choices, one known as peer-to-peer and the other known as client-server. So in peer-to-peer networks we really didn't have a dedicated server. What we had is a bunch of PCs that just were all connected to each other, and that way they could share files back and forth between them and share a printer within the network. Whereas in client-server based networks you actually had a dedicated server. It was a file server, or a mail server, or a print server, and it had some sort of a dedicated function. So on the left here what we're seeing is the client-server structure, and on the right we're seeing the peer-to-peer structure. So just if you're going to set up a client-server network, it just means you've got to determine what type of server functionality you want to provide within that network. And of course you could have multiple servers that each provide their own functionality. And in fact you can actually provide a lot of functions within a single server. It could be a print server and a file server and a web server, all in one. In fact, we should probably point out to you at this point that server and client are kind of a misnomer as far as terminology. In other words, any computer could really be a client or a server. Server just simply means that it's a device that's providing services to the network. And most modern day PCs are capable of doing that, especially the Microsoft operating systems. They have print server capabilities built into them. They have web server capabilities built into them. So you could actually take what would normally be considered a client, your home desktop computer for instance, and you can make it a server. You just simply enable various services to run on that particular computer. So it's not really determined by like the size of the computer or anything like that, although if you're in a large environment, then certainly your servers should have faster CPUs and more memory and large hard drives. So we do normally design servers so that they have more functionality than would your average desktop computer. But the point is, it really is determined by the software and how the software in the operating system are configured on that computer. If it's just simply a client on the network, then a server technically could just be a client on the network if that's all it ever did was just request services. So again, any device that provides services to the network is a server. But anyways, we should get back to this graphic now, but I just wanted to clear up that terminology there. So in a client-server network, you're going to have at least one device that's dedicated as a server, meaning it provides services to the network, and so your network operating system choice is going to be determined by what functionality you need to offer. And again, in most modern-day operating systems, you'll find that pretty much most of the server operating systems, because there are dedicated server operating systems from Microsoft and Linux and even Apple, those server operating systems all provide pretty much the same capability, same functionality. And then, at least what I'm more familiar with is the Microsoft environment. If I want to have a certain functionality like a mail server, then I would buy a special product that I add on to the server operating system. So Microsoft has a product called Exchange. They also have a database server product called SQL. And so you would add these components onto your network operating system, which is either like Microsoft's Windows Server 2003, 2008. So anyway, that's at the software choice level there. We're determining which operating system we're going to choose. And again, you could use XP, you could use Vista, which are normally considered to be client operating systems. You could use those and provide services, basic services, file and print services to your network. Then you got the adapter card choices, and then we get down to the three properties we talked about as far as our network architecture: the access methodology, the logical and physical topology, and also then the network architecture choice. So that's going to be Ethernet in most cases. I don't see anybody really using Token Ring anymore, or ArcNet, or Apple Talk. So 99.9% of the time I'd say it's probably going to be Ethernet. Then we've got the central concentrator, the different wiring choices that we're going to use. Is it going to be fiber optic? Is it going to be Cat5 or copper-based media? And so if you look to the right-hand side of this graphic now, which is the peer-to-peer side of it, really what you'll notice is the only thing missing is the server functionality choice, because you're going to pick basically one operating system, and that's the same operating system you'll probably run on all your clients. Although we can easily intermix all of these. I mean, Apple and Windows and Linux, they can basically all talk to each other these days using TCP/IP over Ethernet. So then at the very bottom, for both sides, it's very similar. I would just say that in the hardware choices, again, with a server, you probably, with regards to your CPU, whatever computer in your company, or even at your home if you want to have a server, whichever one has the fastest CPU, has the fastest and most amount of memory installed on it, has the fastest and largest hard drives, that's the best box to use for your server. And then, of course, on the right-hand side is the CPU choice for your desktop, and you can get away with much slower CPUs and less RAM on just basic desktop. And if you're only going to browse the internet, you don't need a really fast CPU and lots of RAM and large hard drive storage space. So just all things that you need to consider as an IT professional when you're making choices as far as your LAN technology is concerned. So here we have a NIC technology analysis grid. This would be a good form to use when you're considering the purchase of your network interfaces that will be utilized in the equipment in your network. Couple of points over here on the left. Servers should contain faster NICs than do the clients do to prevent bottlenecks. And NICs need to be compatible with the CPU bus. So that means modern day we're talking about, is it 32-bit or 64-bit? The chosen media has to be compatible with the chosen media. It would have to have an RJ45 jack on the back of the network card to be able to have a Cat5e cable plugged into it. If you're using an older thin net network, and then you would have to have a BNC connector. And of course, if you're using fiber, you would have to have the appropriate fiber connector. And then of course the network architecture, the network card, the network interface card definitely has to be compatible with the network architecture. So you're going to purchase an Ethernet card, a token ring card, depending again on the type of network architecture that that particular network interface is going to be operating on. So if you look at the grid over here on the right, then you can see that there are boxes, and as you're looking at a particular component, you would identify if it's Ethernet, token ring, fast Ethernet, Gigabit Ethernet, 10 Gigabit Ethernet, or ATM. Is it an internal interface, an external interface? What's the bus type and the drivers? Does it support UTP, STP, fiber, wireless? And then these are management technology support methods down here. We'll talk about these in a later chapter. But does the network interface card support SNMP and RMON and SMON and PROM and Wake on LAN? And then at the very bottom there you have the pricing. So it just would be a way of analyzing different manufacturers' network interfaces and comparing them to make your final decision on purchase. So now we'll take a look at a few of the individual network architectures that are out there. Of course, the most popular is Ethernet. It was born on May 22nd, 1973, and it was originally based on the Aloha network, which was one of the first networks, if you remember from our history of network architecture slide earlier. And it was invented by Robert Metcalfe. He was an MIT graduate. He developed Ethernet along with a gentleman by the name of Robert Boggs. They both worked at Xero's Palo Alto Research Center, also known as the PARC Research Center, or Xerox's PARC facility. And after he left Xerox, he became the founder of 3Com, one of the largest network interface manufacturers in the world there for a while. They even owned Candlestick Park, the old San Francisco Giants baseball stadium, for a period of time. And so you can see over on the left there's a picture of Robert accepting a National Medal of Technology in 2003. So Ethernet is a frame-based computer networking architecture for LANs as opposed to cell-based. And traditional Ethernet can be defined as using the access methodology of CSMA CD, the logical topology of broadcast. The physical topology historically was a bus, but currently is a star. Ethernet has had three standards in its lifespan. The first standard was known as the DICS 1.0 standard. It was developed by Digital, Intel, and Xerox, and so we just used the first letter of each of those companies and come up with DICS. The second version was Ethernet 2, also known as DICS 2.0, and then the modern day Ethernet is the IEEE 802.3 and 802.2 standard. And so we'll have a graphic coming up later and I'll show you the breakdown on that. But basically 802.3 is the MAC portion, the physical layer components, and then the MAC sublayer, the Datalink layer, and then the 802.2 defines the logical link control sublayer of the Datalink layer. And so those two combined then are what define modern day Ethernet. So here are two versions then of an Ethernet frame, the way that they are made up. And if you look at the far left, this frame would be traveling from right to left, so the beginning of the frame is on the left hand side there. And it begins with a preamble, which is 8 octets long. An octet, remember, is bytes, so we're talking about 64 bits there. And then after the preamble just signals to the network card that there's a frame that's coming, and at the end of the preamble then begins the actual frame with the destination address. So that's where the MAC address would be stored, the 6 octets, in other words 48 bits to represent that 12 hexadecimal value of where it's going to. And then the source MAC address, which would be also 48 bits, again that 12 digit hexadecimal value representing the network interface that's sending the message. And then that's followed by a type field. And the type field then just basically indicates at the network layer what protocol is going to be utilized. So is it TCP/IP, is it IPX/SPX? And so that way the network interface knows which API, which protocol to load up and process the remaining data inside of the frame here. And then at the end is our trailer, and we use that CRC, or frame check sequence, which is 4 octets long to make sure that the frame was received without error. So the encapsulation, again, remember, is the trailer at the end and the header at the beginning with the data contained within there. So then an IEEE 802.3 frame is a little bit different. It still has 8 octets essentially at the beginning for the preamble. They just kind of slightly reorganized it. They reduced the preamble to 7 octets and then had a actual remaining byte there. The last 8th octet, or the last byte, is then to indicate that to give that signal that to the network interface card that the frame is about to begin. And then again, that's followed by the destination address. And you notice now that actually it could be 2 or 8 or 2 or 6 octets. So still 6 representing the 48 bits, the MAC address. But in certain scenarios, it actually can be shortened to 2 octets. And so that's the same for both the source and the destination. And now the big difference in the frame layout of 802.3 when compared to Ethernet frame layouts is that there's a type field in Ethernet 2, but a length field in 802.3 frames. So the length field just basically identifies how many bits are being used to define the logical link control. And again, remember that the logical link control is the upper sublayer of the Datalink layer, and that's the 802.2 specification from IEEE. And what that does is that's very much like the type field of Ethernet 2. It just tells the network interface what protocol is operating at the next layer up. Is it IP, IPX, AppleTalk, some network layer protocol. And then following the logical link control is the actual data itself. So those are all combined together in one field, and so the length field just has to identify how many bits are being used to define the logical link portion, so the network interface knows that the remainder is the data there. And then the trailer is the same. It's still a frame check sequence, and the field size is 4 octets. I should mention too, and the bulleted item here mentions it, that within the LLC portion of the frame, that it includes the destination service advertising point and the source service advertising point. And so that's just, again, really essentially identifying what's going to be needed at the next layer up, at the network layer, to process the remaining data. Ethernet nomenclature. What this is referring to is the use of a format to identify the type of Ethernet network that's being utilized. And so X base Y is the standard Ethernet nomenclature, where X represents the speed of the network. Is it 10 megabits per second, 100 megabits per second, gigabit speed? So X is the speed, followed by the transmission type. And in Ethernet, it's always baseband transmission. You have 2 types of transmission, baseband and broadband. In broadband, that's very much like your cable television. You have multiple frequencies that travel in one direction. In baseband, you only have one frequency, and it travels in both directions on the media simultaneously. So that's what the red bullet tells you there, one frequency traveling in both directions simultaneously. So that's the transmission type. So we follow the speed by the transmission type, and then the third part of the Ethernet nomenclature is the media type. And so if I were to say 10 base T, that would mean 10 megabits per second using baseband transmission over twisted pair cabling, the media type. So this slide is a typical fast Ethernet architecture. Fast Ethernet generally refers to 100 megabit per second Ethernet networks. And it really isn't the most up-to-date graphic because it shows hubs being used here instead of switches. So where we see hubs basically today, we would actually see switches in operation. But of course it is using dual speed hubs or switches, and so that means that each port as well as each interface that's attached to either the servers or the PCs, the desktops, they can sense the speed of the traffic and adjust accordingly. So if it's receiving 10 megabit per second frames, then it will slow its speed down to 10 megabits per second. If it's detecting 100 megabits per second, then it can adjust and speed up and handle the 100 megabit per second traffic. So it's auto sensing both on the switch ports as well as on the modern network interfaces. And then also, of course, we're using an extended star topology here. Remember, star is where everything branches out from a central concentrator. So in this case, it's called an extended star because we have several concentrators. So that if you look at it from the top down, we've got 100 megabit per second Ethernet cards in the servers connected to a switch, which then is starred out to two other switches. I know the graphics say hubs, but it should be switches. One is operating one switch, the one on the left there, 10 megabits per second, the one on the right, 100 megabits per second. And then coming out of the left-hand switch is three computers. They're all operating at 10 megabits per second. So the limitation in this particular case actually is the switch itself. So the switch is limited to 10 megabits per second. It's not capable of adjusting to higher speeds. Whereas the switch on the right and also the switch, the top switch there, both are the auto sensing type. So they can operate at whatever the speed is of the network interfaces that's attached to that port. So you can see that one desktop on the left there is operating at 10 megabits per second, so obviously that port is operating at 10 megabits per second, and then the other two computers are operating at 100 megabits per second, so those ports are operating at 100 megabits per second, and then of course between the two switches, the top one and the one on the right, those two ports are operating at 100 megabits per second as well. And so again, you'll notice the nomenclature here of 100 base T and 10 base T, so that's indicating the speed of the network, the transmission type, and twisted pair cabling being utilized. These days, a lot of networks are using Gigabit Ethernet, also known as 1000 base X. And so this is an upgrade to Fast Ethernet, was standardized in IEEE 802.3z. So that's just an actual document that is the specification for Gigabit Ethernet. And as I said, it's known as 1000, which is a gigabit, 1000 base X. Notice that though the X can be replaced by several different types, and that's the three red bullets we see at the bottom of this slide. So SX would be your short wavelength laser multimode fiber optic media. Primarily that's used in the horizontal building cabling. That means running between rooms or running between buildings. And then your 1000 base LX is indicating the long wavelength laser single mode fiber optic media, primarily used for the high-speed campus backbone. And then the last would be your 1000 base TX or copper base. So the first two are fiber, and then the last one is copper based, and that would be using Cat5e unshielded twisted pair with a maximum distance of 100 meters. And usually that's what we use to connect the servers and the switches to, I should say the servers and the desktops to the switches. The next architecture we look at is token ring, not really utilized too much anymore. Again, we've seen some of this discussed before, so to kind of summarize, the access methodology is token passing, its logical topology is sequence. The message is passed from one machine to the next, to the next, to the next, until it gets to its destination. The physical topology uses a central concentrator and is connected by cabling coming out of it. It's called a MAU, but it looks very much like a switch, and so it uses a star topology, physical topology. It's defined by the IEEE in their specification 802.5. That's known as token passing on a star topology. And at one time it was very much in contention for dominance in the marketplace, in the networking marketplace, with 802.3 Ethernet. But once switches were added into Ethernet networks, speeds increased dramatically. Ethernet pretty much took over. So as I said, new installations, very uncommon when it comes to token ring. Another network architecture that was expected to really take over the networking environment was the asynchronous transfer mode, or ATM, on LANs. And ATM was very popular in the wide area networking, and so the theory was that it would also move into the local area networking as well. And it is a switch technology, originally developed, as I said, for WANs. And when we use it in a local area network, it's referred to as ATM LAN emulation, also known as ATM lane. And so lane was required for mixed environments, and the MAC addresses there had to be translated into ATM addresses, because ATM is a cell-based format. Remember that Ethernet and MAC at the Datalink layer is frame-based. And so there needed to be a conversion there between the MAC addresses that were used on the local area network into the ATM addresses then that would be used in the ATM lane emulation. Wireless networking, of course, is quite popular these days, and we can build an entire local area network using nothing but wireless technology. So IEEE specification here is 802.11, and then of course there's several different flavors of wireless technology, 802.11a, B, also there's N in draft right now, and I'm missing one, well, G, which came out after A and B. The access method was still CSMA CD at the Datalink layer, and more specifically the MAC sublayer of the Datalink layer. That's where the access method is defined. And then 802.11 frames are similar to our 802.3 Ethernet frames, so very compatible with the current Ethernet market in usage in local area networks. The 802.11b specification was 11 megabits per second, and that was the theoretical speed on it. The practical, in other words, the real speed we actually got out of it was 4 megabits per second. And it used the 2.4 gigahertz radio frequency bandwidth, and that was very much subject to interference from common electronic equipment, including microwaves. And I think I mentioned to you earlier that Bluetooth runs in that same frequency range as well. It was a shared access method, so multiple devices could be using the same airwaves simultaneously to try and communicate between a transmitter and a receiver. And so it definitely was sensitive to the increased number of simultaneous users. The more users you got, the more likelihood of collisions. And so that is a little bit problematic within wireless LANs. Very commonly available. It's also quite inexpensive, and the range is measured in hundreds of feet. And of course it's lower indoors because you have to go through solid objects in many cases. 802.11g interoperates with 802.11b, and it basically was a speed increase to the B technology, so it got it up to 54 megabits per second theoretical. Uses the same frequency range of 2.4 gigahertz, and it's also very common, inexpensive. The latest standard is 802.11. It's actually, I should say 802.11n is not the latest standard. It's still in draft stage as of this point in time, but a lot of companies have released a version of either wireless access points that support 802.11n or network interfaces that support 802.11n. And the unfortunate thing is that a lot of manufacturers' 802.11n implementation is not compatible with other manufacturers' 802.11n. And so once the draft becomes a standard, that should be resolved. But right now, as of this moment in time, that can be kind of problematic. The advantage you can see that we're going to get here is much higher speeds on wireless LANs, up to 600 megabits per second. And we haven't talked about this before. I want to take a quick opportunity here to point out that we're looking at, when you look at the speed here of 802.11n, or any of the speeds that we've talked about, even the 54 megabits per second, notice that it's capital M for mega, lowercase b for bits. If that was a capital B, it would be bytes. So that's important for you to know the difference when you're looking at specifications. Lowercase b is bits. Usually when we're talking about data communications, we're talking about bits. And then uppercase B, capital letter B, would be bytes. So usually storage is, and memory is rated in bytes. So megabytes would be, your reference to memory or hard drive size. And when we're talking about data communications and speed of transmission, we're usually talking bits, lowercase b. So this graphic is just showing you that in wireless network operation, you can have multiple devices operating on the same channel as long as those two channels don't overlap. So in the graphic on the left, you can see there's actually 4 devices in operation. 2 of them are using channel 1 and the other 2 devices are using channel 2 and channel 3. So even if the 2 and the 3 overlap, or in this example the 3 and the 2 overlap with 1, there's not any interference there. And as long as there's separation between those devices that are using the same channel, channel 1, then everything's going to work okay. But then the graphic on the right is showing you that here now we have the 2 devices, their signals are overlapping each other, so the devices are a little closer together. So since they're both using the same channel, channel 1, and they're a little bit too close together there, then there's a little bit of interference with their signal. Wireless LANs have hubs, and those hubs are generally used as access points or as bridges. And so if you look at the graphic on the left there, you've got a server that's hardwired to the hub, and then the hub also has a link to the internet. So this is pretty common in most households these days. Well, you may not have the server, but the router, your Fios router, your UVerse router, your DSL router has a connection to the internet, and then it also has a wireless capability so that your computers that you use in the home can use wireless to communicate through that router, that hub there, and out to the internet, or in the case of the graphic, also to that server that's attached to it. So that's giving access to the clients to the network here of either the internet or the local network that has the server on it. In the right-hand graphic, we're looking at utilizing the access points as a bridge. So we've got 2 different hardwired networks, wired network A and wired network B, and then the wireless access points, which you can see are attached to each of those LANs, are providing the connectivity between the 2 LANs, and so that's known as a wireless LAN bridge. One of the big advantages of wireless LANs is that we can have portable devices roaming and continue to maintain access with the particular network that they're communicating with. So in the first example, the graphic on the left, we've got a portable laptop, and it's communicating to the network through access point number 1, and then as the user is moving around and is roaming with that laptop, he moves into the second access point range. And so the point here is that whatever access point is closest to the device, it will automatically switch over and it'll maintain connectivity within the network. So this is a good graphic here because it shows you all these technologies that we've been talking about and really how they map out to the OSI model. So everything that we've talked about has physical layer specifications to it. The type of connector that we're using, the type of media, the format of the signal. Is it going to be using electrical pulses or light pulses or radio waves in the case of wireless? So that's all done at the physical layer there. And then as far as Ethernet is concerned, they all use the same MAC sublayer addressing. They all use that 48-bit or a 12-digit hexadecimal MAC address, and then they also all use 802.2 as their LLC sublayer. So that 802.2 specification, again, remember, just says here's how we're going to connect to the next layer up, the network layer, which is sitting there up above the Datalink layer. And the only exception to that is that the first 2 Ethernet versions, the DIX Ethernet and the DIX2 Ethernet, They didn't have that 802.2, the LLC sublayer. Remember, they just simply had the type field when we're looking at the format of the Ethernet frames. It had the type field instead of the length field. So 802.2 represents the length field within the frame. And again, DIX didn't have that. It just used the type field. So we finished looking at the individual architectures that are available for local area networks. Now we're going to take a look at some of the equipment that is used, starting with hubs here. And so there's different types of hubs: stackable hubs, standalone hubs, and then also we want to talk about the 5-4-3 rule. In fact, let's start with the 5-4-3 rule. The 5-4-3 rule says that you can have a single local area network that is made up of 5 segments of cable connected by 4 hubs, with a maximum of 3 of those segments of cable being populated with network interfaces. And so that's just a specification set forth by the IEEE. I've been in environments where they've, just to extend the length of the network, you know, to go from one end of the building to another, they kept using hub after hub, which again, remember, is like a multi-port repeater, so they had the right idea, but you can actually have too many hubs, and it actually causes communication problems then within the network. So a maximum of 5 repeaters or 5 hubs is really allowable in one single local area network. Stackable hubs, the idea here was that to be able to expand your network, because you've got, you know, port density within your hub. If you run out of ports, you want to add another hub but still have it all together in the same LAN. So these stackable hubs had special ports that allowed you to connect the hubs together so that they would be treated as if they were part of the same local area network. And then, of course, you just have additional ports then that you can plug in your network interfaces to. Standalone hubs are just that. It's just a single hub that's not connected to anything other than just other network interfaces, other computers, and so all the computers attached to that hub are just a single local area network. And also the point they're making here is, in that bottom graphic, is it only has one media type. The top, the stackable hubs there's actually 2 different types of media being used there. There's the standard Cat 5 or 5E cable in those RJ45 jack slots you see, or ports, and then those elongated slots we're using usually proprietary cabling to make the connection between the hubs. And so just different media types, different connectors being utilized to make that stacking capability work. Another type of hub is an enterprise hub. These are usually mounted into telecommunication racks, and they have this big empty chassis that has a circuit board, kind of like a motherboard, in the back of it. And if you've ever seen a motherboard, if you picture the slots that you plug your cards into, that's kind of what this circuitry looked like in the back of this open chassis. And then inside of that chassis you would slide in your various components. So as you look at this graphic here, for instance, they've got one card that is a fast Ethernet card that they've slid into this chassis, and then next to it is an ATM card that got installed into that chassis, and then next to it is a Gigabit Ethernet. And then on the far right is a management module, which will let you hook up a PC to it through a serial port usually, and communicate and manage, actually control the components then that are installed in this enterprise hub. Some of the other things that you notice here too is it has dual fans, redundant fans, so that if one of the fans dies, you still have another fan so that the unit doesn't overheat on you. Generally they would have redundant power supplies too, for the same reason. If one component fails, the components, if one power supply fails, the components in the enterprise hub could continue to operate. And usually those are hot swappable, or in the modern day they're hot swappable. You can just pull out the fan and plug in another one, pull out a power supply, plug in another one. And of course the advantage we get here too is that we can mix and match all these different types of network architectures and media. So here we just simply see a functional comparison between different types of hubs. And again, remember that at the very basic essence, you have what is called a repeater. And the whole idea of a repeater is to connect two lengths of cable together. Because remember that as we go over a certain distance on our media, on our cabling, we will get attenuation, at least in a copper-based environment. That's a real big issue. And so a repeater will retime and regenerate the signal and then put it out the other side and allow us to extend the length of our network. So repeaters in the early days just had two ports, one on each side, but then they started to have multi-port repeaters, which really turned into be hubs. And so then of course we looked at standalone hubs, we looked at stackable hubs, we looked at enterprise hubs. We didn't really look at MAUs, but MAUs are very much like a hub. They only difference is internally they have the structure to make to form the ring. Remember that those are used in token ring networks, and so what it does is it connects the incoming signal from one port to the outgoing signal on the next port, and then that port's incoming signal goes to the out on the next, and so on and so forth. So it actually forms a ring, because remember again, in that ring environment it's sequential passing of the data, and so that's how all the ports are connected together. Whereas in the other standard Ethernet environment, remember it's broadcast based, and so the signal goes in one port and it's forwarded out simultaneously of all of the ports. So in this case, again, just taking a look at where you generally find these, the different network architectures that are supported by them, whether they're standalone, cascadable, they have a modular chassis, if they have any inner networking modules, if it includes WAN links, if it includes network management capabilities, and they've actually filled it in here for you. But I would argue that this is what you are wanting to analyze when you go out and you look at these components, and you go to the Cisco website or Linksys or all the different companies, D-Link, that offer this type of equipment. You're going to want to make these comparisons for yourself and determine which is going to be the right device for your network. Of course, I pretty much am arguing too that you're not going to be using a hub these days. You're going to be using a switch. Kind of a quick overview here of network management. We actually have a whole chapter where we cover network management, but there's a special protocol that you want to start getting to be familiar with. It's SNMP, the Simple Network Management Protocol. And that is in most high-end devices. Now the little link switches you buy for your house and D-Link and those type of things usually won't have the SNMP or the management capability built into them. But your high-end stuff that's used in enterprise-based networks, usually, in fact, that's one of the things when you're looking at the specs, if it says it's a managed switch, usually that's what it means, that it supports one of these management protocols like SNMP or RMON. And so the idea is that you have this management system, which is kind of right in the middle of this graphic, and that's just a computer running management software, and it connects to in this case, the enterprise hub, and then also the stackable hubs on the right there are also connected through the enterprise hub to the management system. And a software component called an agent is really a signal or a message coming from the device that then gets received by the management system. So the management system is collecting all this information sent to it by the agents of these various components. And so that's how we can track how many frames per second that are traveling through a particular device, and how many errors that might be occurring with those frames as they travel through the device. So all kinds of data can be collected about these devices, and then it's stored in a database. And you can see in the top left there, it's called a MIB, a Management Information Base, when we're talking about SNMP management systems. And so again, we've got a whole chapter on that coming up later on in the course. This graphic illustrates the problem I was telling about with regards to hubs. It's a shared media device. So all of the devices connected to the hub here are sharing this same backbone. That's kind of this gray box, the light gray box they're showing inside of it. And they've got one workstation then transmitting, sending a signal in, and that message is destined for the server on the far right there. But while that communication is occurring, all the other devices that are connected to that hub aren't allowed to transmit. So it's sending that shared media is very much like a party line. You know, you can imagine, I don't know if you're familiar with a party line, but that's in a telephone system. If you have like all your neighbors all connected to a party line, that means that you can all, if you pick up your phone, you can all talk to each other without actually dialing each other. So in other words, your neighbors could actually listen in on your conversations when you do call other people. And so, you know, that's kind of like what a hub is, the fact that you've got them sharing the same connectivity. The media is all shared, and so they have to take turns talking to each other, otherwise you just get a big mess going on. Of course, the terminology we've explained to you is called collisions, when we have two devices trying to communicate at the same time in that type of an environment. The other thing too is with the shared media, you do get a fixed bandwidth, meaning that if one device is running at 10 megabits per second here, then all of them would have to run at 10 megabits per second, even if they had 100 megabit per second network interfaces. So one device can slow down all of the devices that are connected to the same media. So now we get to the switch, which, as I've said many times, is the device you will most likely use in the modern day network. So the advantage you get, of course, again, is that you can have multiple stations transmitting simultaneously, and you don't have that situation that we just talked about with regards to the hub. If any one of these devices are running at 10 megabits per second, having it slow all of the other devices down, you actually have the ability to run multiple speeds through the same switch. So you can have some devices operating at 10 megabits per second, some at 100 megabits per second, and if you had the right switch, even some at gigabit per second. So really the network interface on the workstation or the server would really dictate the speed of that particular device, but would not affect the speed of all the other devices attached to that switch. Which you can see they've actually misidentified these graphics. I hadn't noticed that before. They're calling it a switching hub. Generally you won't hear it referred to as a switching hub. You'll just hear it referred to as a data communication switch or a LAN switch. So a reiteration of something I mentioned to you before, how LAN switches work. They can actually process the data link layer, or specifically sublayer or MAC sublayer information. So the switch can read the ports. It actually, what it does is when you plug devices into the switch sends out a little message, and it gets the MAC address from that device that you've attached to it, and then the switch will store that in its LAT, its local address table. And so the local address table just basically consists of, here's MAC address A, and it's attached to port 1, and here's a MAC address B, it's attached to port 2. So every time a message comes into the switch, it looks at that local address table, and it can figure out, based on the destination of the message, which is the correct port to forward that message out of. So it is important too, let me reiterate that when we're talking about repeaters and hubs, those are considered to be physical layer devices. They cannot read the MAC sublayer. They cannot read the MAC address. All they simply do is forward the electricity, or forward the pulses of light, or forward radio waves, if it's a repeater or a hub. If it's a switch, then it is capable of reading the data link layer MAC addresses. So it's a layer 2 device as opposed to the repeater or the hub, which is a layer 1 physical layer device. So interestingly enough, switching, the terminology actually refers to the fact that a switch, being a data link layer device, is capable then of processing the destination MAC address, actually reading the MAC address that the frame is destined to, and then making a forwarding decision to forward the frame, the incoming frame, to the correct port where that particular device that matches that destination MAC is attached to. Switches are also considered to be transparent devices in that the ports themselves don't have any MAC addresses. So they just simply receive all of the frames that are being transmitted by a device and then look at the destination MAC, look at that, compare it, I should say, to their LAT, their local address table, and then figure out which port to forward it out of. We're getting kind of redundant here, so just reiterating what we just talked about as far as switching is concerned. Again, the switch is checking the source address of each frame that it's receiving and adds the source address to its local address table for that port. So that's how it originally builds the local address table. As frames come in and it looks at the source address, it says, oh, okay, that's MAC address A, that's coming in on port 1, so that's where that device is attached. And then, of course, the switch is learning as it's going there without having to have an administrator manually actually reconfigure that, manually type in the routing table information about any new information or any new workstations that might be added to the network. So as you plug in devices or unplug devices, then the switch is adapting dynamically, automatically. And then finally, we're going to take a look at the way that switches forward the frames that it's receiving. The first method is referred to as store and forward switching. In this case, the switch reads the entire frame into its memory first before it actually forwards the frame to the port that has the destination device. So in this case, the advantage of it is that we are reducing the number of bad frames that might be forwarded. The problem with it is that it takes more time because it has to read all the bits that make up the entire frame. See, frames are variable length. They can be up to a maximum of 1,518 bytes in length. That's called the MTU, the maximum transmission unit for an Ethernet frame. And so the frame could be any length, and the switch has no idea to begin with what that length is going to be. So it has to wait and receive all those bits before it can make a decision how to forward it. So it does slow down the process a little bit. But again, the advantage is it also knows whether the frames are bad or not, and it'll discard any bad frames. In the second method of processing that a switch can utilize, called cut-through switching, the switch is only going to read the header, the addressing header information. So it sees the source and destination address and then immediately forwards it to the port that message is destined for. So obviously now, since it's not reading the entire frame, it's much quicker. The drawback, though, is it doesn't recognize whether that frame is bad or not before it forwards it out the destination port. And the final method is error-free cut-through switching. In this case, it's using an adaptive switching method. In other words, it can analyze the traffic that's going on through the port there and know which switching method is better to utilize, either the store and forward or the cut-through switching method. Because there's sometimes you get interference on a particular line, and so it may require the store and forward method, whereas another port may be error-free 100% of the time, and so then cut-through switching would be more advantageous there. And so obviously that's the best method when it can really recognize for itself which method is going to be most appropriate for the given situation. So this last slide here is illustrating the advantages of using switches, at least one advantage that we really haven't talked about, which is using the switch to kind of segment the network as far as breaking it into smaller chunks. They're still all part of the same broadcast domain. Even though you got the three different boxes here with the groupings of computers, any one of those computers can send a broadcast message out that would be received by all of the other computers that we see here. In this case here, though, what they're kind of doing is breaking it down based on the speed. They've got one switch, it's 100 megabits. Actually, all of the switches, if you look at them, are all 100 megabits per second, and then they're tied into a gigabit per second backbone. So that way the backbone can handle the traffic, and then each local switch can because if you think about the communication process here, in the top left gray box, if the first computer sends a message to the second computer in that same gray box, the message is going to go in the switch and then out the same switch. It doesn't have to go on to the backbone, that gigabit backbone on the network there. So see, it's kind of somewhat isolating the traffic of these multiple devices. So if you look at any one of these groupings here, the same would be true. If the one device attached to a switch is going to send a message to another device attached to the same switch, we're able to communicate, and we're avoiding putting the data onto the main backbone of the entire network. But if we need to cross that backbone to get from one of those gray boxes, say, to the servers there in the red box, then we're capable of doing that as well. So it's one way of reducing traffic on your overall network. And so that's the last slide for this chapter, Chapter 4. So we'll talk to you again in Chapter 5.